everyone. I'm Rollie Goodman. Some of you may know me. And I'm here to talk to you about some of my recent work at the MSU TechLink Center, and more broadly, what some of it could imply to the Montana tech community as a whole. So TechLink, if you haven't heard of it, is an organization with a really interesting and unique purpose. It exists to help Department of Defense labs connect with businesses, and in particular small businesses, in order to help facilitate technology transfer. So what this really means is DoD labs patent a huge number of technologies across a whole bunch of sectors. And by helping small businesses license these inventions from the labs, we're able to do two things. So one, we're able to make it possible for these inventions to actually come into production. And two, we are able to allow the broader industry to benefit from the innovation going on in these labs. So there are over 100 such DoD labs, and there are thousands of relevant inventions. So to keep track of them all, we maintain a database based on US Patent and Trademark Office data. So then a question we end up with is, how are we going to help these customers, in case these small businesses, find technologies within this database that they might want to license? So recently, a lot of the answer to that has focused on improving customer experience in different ways, and this is particularly focusing on our online presence recently. So our goal here is to make it as easy as possible for customers to independently use our website to find technologies that they might be interested in. So a great example of the importance of this actually just happened back in March. There was a marine construction consultant who was from New Jersey, who's on our website, and he found a new technology from the Navy that can detect microcracks in steel without having to actually cut into it. So 13 working days later, thanks to our new Express licensing portal, which is another project we've had going on, the consultant had the rights to the technology and was able to start product development. So this is pretty much unprecedented. The licensing process often takes years normally, so 13 days from application to completion is, as far as we know, the fastest transfer of this type in history. But the improvement in experience actually started well before the consultant submitted the application in this case. So the consultant was able to find this technology by narrowing down our database to his industry area, and that's where a lot of my work comes in. So before we get into details too much, I wanted to give a quick idea of my background and why my experience is relevant here. So my undergraduate degree was actually in economics, not computer science. I discovered CS late in my degree, essentially by accident. I sort of like fell into it. And I wanted to add a second major, but at that point it was my junior year. So after I received my bachelor's degree from Lewis and Clark College, I came back to Bozeman, where I grew up, and I had the intent of just finishing the second undergraduate degree at MSU. So I walked into Dr. Paxton, the department chair's office, to set up just taking a few classes, kind of seeing how things go. And somehow 20 minutes later, with no intention of doing this, I left having fully committed to do a master's degree. Yep. Some of you guys might know how that goes with Dr. Paxton. It's like these Jedi mind tricks. It's incredible. So during the course of that degree, which I had then committed to, I was advised by Dr. John Shepard. So he's the director of the Numerical Intelligence Systems Laboratory. And this is a collaborative lab between MSU and Johns Hopkins. And it focuses on research areas in AI and machine learning. So machine learning kind of had a natural draw for me just because it tied in a lot with game theory and other aspects of my economics background. So it was a pretty natural choice for me to pursue these research areas. And it was actually through a graduate research assistantship in this lab that I was first introduced to TechLink, which is how I ended up learning about the project that I'm here to tell you about. So back to the present, currently our website has over 5,000 licensable technologies that users can look at, and the database is constantly growing. So how do we help users find the ones relevant to them? Historically, this was kind of a targeted marketing effort. It just required, we have like a lot of patent lawyers and stuff working for us, and it required them to know the different companies, the different technologies, the different labs, sort of have connections in different places. But we decided a more efficient way would be to have users able to find relevant technologies on their own. And one of the most important ways we can do this is to divide technologies into industry categories. So these are the ones we use from our website. And so this might seem like a really simple and obvious step, like, yeah, duh, of course, you want to be able to indicate a patent subject matter to the people looking at them, but it's actually deceptively problematic to do by hand, and this is for a couple reasons. So first of all, this information doesn't come to us with the other information we get about the patent. It has to be assigned in-house by somebody with domain knowledge, because the differences that might put a patent or technology into one category or the other can actually be pretty subtle, and a layperson might not know them. Also, it's really time consuming. So this involves, for a human, sitting down, reading a whole bunch of information about each patent, making decisions individually, and you can't really just do it once and be done with it. This is an ongoing process. There are constantly new technologies coming in. And then finally, it can also potentially be inconsistent. We found that two people, or even the same person on different days, could look at the same patent, but potentially come up with different ideas for how they wanted to categorize it. So all of this combined is going to make the process a really good candidate for automation. It's going to be lower maintenance, more efficient, more consistent, and it'll also be able to learn from itself and improve over time. And so I'm guessing many of you already have at least a passing interest in AI and machine learning, given that you chose to attend this talk. So I'm assuming it wouldn't be too hard of a sell to convince you that this is something we should pursue. So just in case anyone here isn't familiar with the terminology, as we kind of move into the more machine learning part, what we're doing here is we're working with a classification problem. And for a classification problem, really what you're looking to do is label new data. For this, you need to have a set of previously labeled data. This is going to be called your training set. In our case, we had over 9,000 patents that had already been hand categorized that we could work with. So the goal here is to extract patterns or information from features of this training data, and then use those to create a model that can generalize and label new instances correctly. So here's a peek at what this training data actually looks like that we had to work with. This, by the way, is actually one of our currently available technologies. So this is just a small sample of the large number of features that you're going to find associated with each patent. And we did some experimentation to see which gave us the most information so we could decide what to include in our classifier. So sort of counterintuitively, you don't actually want to include every piece of information you get in a model. Some might not add a whole lot of information, some might just be confusing and not really have a pattern, and some can make computation really expensive. So here's what we found worked best for our purposes. So first were the title and abstract of the patent. These are pretty self-explanatory text fields. They describe the content of the patent. They're going to function pretty much how you'd see a title and abstract function, like in a conference paper or anything similar. And then there's another piece of information included with the patents that we found to be really information dense. And these are what are called Cvc Codes or Cvc classes. So I'm willing to bet that few, if any of you are familiar with these. I definitely was not before I took on this project. So here's kind of what they are and how they work. CPC stands for Cooperative Patent Classification. It's a system of patent classification that came into use in January 2013, and it's used by both the European Patent Office and the US Patent and Trademark Office. And each patent under this system is going to be assigned at least one of these classification terms. Here you can see we have several. That's kind of more the norm. And each one is going to have a hierarchical structure that's easiest to explain with an example. So here we're looking at just a single CPC term, and as you read it from left to right, it goes from more general to more specific, and it builds on itself as it goes. So the first letter is the section, and this gives you a really broad idea of the subject. There are only 9 possible values, so it's pretty vague. So this one is going to indicate human necessities, so again, really broad. The next 2 digits are going to be the class. That's going to get more specific, so in this case it says, all right, these are human necessities and they're used for agriculture. And then after the class is a single letter for a subclass, more specific, these are agricultural tools that are going to be used for working soil in this case. And then after that, we're going to have a group, which is 1 to 3 digits, a slash, and then the main groups and subgroups. And as those go along, they're going to progressively get more and more specific. So finally, the way you'd read all of this together, and I definitely took my notes for this, would be walk behind agricultural tilling implements with rotary-driven tools, with tools on the horizontal shaft transverse to the direction of travel. Hearing all this, you can kind of see why CPC terms are a really interesting feature to work with. So they're really, really information dense. But at least to me, there wasn't really a clear sense of how you want to treat them right off the bat. At first glance, they seem like they could be sort of like keywords, but then they're almost more of a code, and they've got this really rigid hierarchical structure, so you can't really treat them exactly like traditional keywords. And so because they were really interesting and really unique, building classifiers specifically to work with these CPC terms was the first step that we took on in this process. Ultimately, we decided they were kind of more like keywords than they were like anything else we could categorize them as, so we leaned toward treating them as keyword-like. But unlike traditional keywords, we had to decide on the specificity level. So even just from this one example, you can see there's a really, really fine granularity if you use the entire term. It's really specific. This is really helpful if you're looking at individual patents like as a human reader and trying to glean what it's about. But it can cause a lot of problems when you're trying to learn a model that can generalize effectively. So there's a known issue in data science, and it's a big issue, called overfitting. And this is essentially when your model is going to memorize the training data instead of extracting broader patterns from it. And if this happens, what you'll see is you'll get really, really good results on your training data, but then when you throw new instances at your model, it will perform really poorly. So this is particularly going to be a concern when you're looking at the number of feature values versus the amount of training data you have. So yes, we had over 9,000 patents to learn our model from, and that's pretty significant. But if we also have thousands and thousands of highly specific possible values for our features, we could still run into problems here. So to decrease the likelihood of this happening, we decided to decrease the specificity. And the amount of information we wanted to include or exclude was very much trial and error. But we found that we got the best information to generalizability trade-off by getting rid of the main group and the subgroups. So we just kept the stuff in red, everything before the slash, and discarded the rest. So from here, we needed to get the Cvc terms into a format that was easier to work with. So we utilized Python's scikit-learn library for our underlying classifiers. If you guys haven't heard of scikit-learn, it's a really fantastic open source machine learning library. You'll hear about it used a lot both in academia and in industry. And as someone who has implemented a lot of the algorithms it provides by hand completely from scratch in the past, I really can't recommend it highly enough. It saves a ton of time. But scikit-learn's algorithms require vectors of numeric data. This is pretty standard for most of these types of algorithms. So we had to come up with a process to turn these Cvc terms into that type of data. And that sort of came as follows. So let's say, to keep the example tractable, that these are the only 5 Cvc terms in the entire training set. Of course, we actually had thousands, but we can pretend for now because I can't fit that on the slide. So this is going to be called the vocabulary. Sometimes it'll be called a dictionary. There's a bunch of different words for it. Then let's say we have this particular patent which has these 3 Cvc terms. So the first thing you want to do is you want to truncate the terms like we talked about. So we have to get them down to the right specificity level. After that, we want to transform them into a vector. The length of the vector is going to be corresponding to the length of the vocabulary, so in this case 5. And then each enter in the vector is the number of times that that specific term from vocabulary appears in this instance. So our vectors of length 5, you can see only 2 of the 5 terms actually appear in this instance. One appearing in 038 appears twice, one ending in 039 appears once, the rest of the entries in the vector are 0. So once we've transformed all of our Cvc data this way, we were then able to test out some common classifiers and see what gave us the best results on this data. And what ended up performing best for us is what's known as a support vector machine, or an SVM. I'm not going to go crazy deep into the mathematical underpinnings of these for your sake as well as mine, but here's a quick overview of what an SVM actually is. So the general idea of an SVM is that you want to plot your training data as points in an n-dimensional space, where n is the number of features. So in this case, we have 2 classes, the ones represented by purple circles and then red squares. And so here are, we would have a 2-dimensional space, 2 features. And then we're going to find the hyperplane that best separates the 2 classes. And this is done by selecting the separator that has what's called the maximum margin, or in other words, the maximum distance between the nearest data point of either class and the separator. So in our example, the maximum margin separator is going to be A here. If you were to take like line B, for example, you can see it gets much closer to different points from the training data. Unlike in our example, though, there's no guarantee that there's actually going to be a linear separator between the classes. So like, consider this example. There's no one straight line that's going to separate the purple and the red points in this case. So in cases like this, an SVM is going to apply what's called the kernel trick. And this essentially projects the data into a higher dimensional space where you can separate the classes with a hyperplane. So like, say, sticking with this example, we were to project this data into 3 dimensions, and then maybe it's going to look like this on the XZ axis. Then in this case, the data is linearly separable. You can now put a linear separator in there. So you might notice that in this original form, we're talking about 2 classes. So an SVM is a binary classifier. But for our application with labeling patents, we have a multi-class problem. We had 11 categories total to work with. So there are a couple different ways you can modify the algorithm to accommodate this, and the one we chose does what's called one versus the rest classification. And what this means is that it's actually going to train a separate model for each class. Each class's model is going to learn a separator that separates that class from every other class combined, hence one versus the rest. So one really nice thing about SVMs is that they're unusually resistant to that overfitting problem that we talked about earlier. There are a couple of reasons for this. Probably the most intuitive is that by maximizing the margin, they're going to penalize fitting really closely to the training data. So it's going to make it less likely that you're going to just memorize it. So this doesn't mean an SVM is never going to overfit, but it is more resistant than a lot of other types of models. They're also known to be effective in high dimensional spaces, which is absolutely a concern for us because, again, even with having taken the specificity level down, we still do have quite a few CVC terms. So as we were selecting our algorithms like this, our parameters, things like this, we took another step to try to avoid overfitting using what's known as cross-validation. So for those who aren't familiar with this, the process is you want to take your training data and you want to randomize it because you don't want any effects from, like for example, our data came in chronological order. You don't want that to impact it, so randomize everything. And then you're going to split the data into k groups. Oftentimes you're going to see k equal to 10. For here I have k equal to 5, so that is at least readable. Then you're going to run k experiments. Each time you're going to train the model on all except one group. So in this case, the model or the group that's held out is going to be in blue. And then you're going to test on that final group, and you're going to rotate through so that each group is the test set exactly one time. And then you're going to average over the accuracy measures from those k experiments to get your overall accuracy measure. And I should note, it doesn't necessarily have to be accuracy. It can be whatever evaluation metric you're looking at in this case. So it's important to do this way because if you only evaluate on a single test set, you could potentially end up with a really biased view of the accuracy based on what just happened to end up in the test data. So like for example, if you got really lucky and you had disproportionate number of like easier to classify examples of the test set, you might end up thinking your algorithm performs much better than it actually does once you get it into production. So using this cross-validation process with a support vector machine on our Cvc data, we were able to get about 87% classification accuracy. And we were already like pretty pleased with this result because it was on par with, actually slightly better than previous attempts by third parties. But we knew there was more data we could combine with these results to further improve the model. So to further explain our next steps, I want to introduce the concept of an ensemble method. So ensemble methods refer to a machine learning technique that's going to combine multiple base models into a single larger model for prediction. And these component models can be different versions of the same base algorithms, or they could be completely different algorithms. And these are often going to offer an increase in robustness and generalizability over single models. And this is particularly useful when, like in our case, you're working with diverse types of data and solving the same problem. So ensembles can potentially reduce the impact of bias of individual classifiers. So they can potentially be very powerful. And in practice, we've seen in recent years that they've been winning quite a few competitions in machine learning, pretty high profile ones. And I should interject with a quick note about what I just said. I mentioned bias. It's important to remember all machine learning algorithms do necessarily have bias. Otherwise, generalization is impossible. So bias is not necessarily a bad word, but it is a trade-off that does need to be managed, and ensembles are one really effective way of managing that. So at this point, we already had one of our component models for an ensemble that we just described with our Cvc terms. So our next step was then to describe another one to work with the other features that we selected, and this was our text data, and then to find a good way to combine them after that. So we proceeded with the text features of the document in the title and the abstract. Processing text data is a pretty well-studied problem in machine learning in general. So unlike the Cvc data, we had a pretty good idea of how to proceed right off the bat. Much like in the case of the Cvc data, the goal is that you want to get your data into a vectorized numeric format that the algorithms can work with. And the easiest way to do this would be, like in the Cvc case, build a dictionary of all of the words that occur in all the documents, and then transform each document into a vector representing the occurrence or frequencies of each word or term drawbacks. So first one, if you do this, you can end up with hugely long vectors of words. many of which might not actually give you very much information. So for example, consider words like a, and, the, it, and so on. These are going to appear in pretty much every document, so they're not actually going to give you any help in drawing out useful characteristics about to use in classification. So these are called stop words, and removing stop words is a pretty key part of pre-processing text data. Scikit-learn has a built-in English stop word list. Most other tools useful for natural language processing do as well, so like Elasticsearch, things like that. And getting rid of stop words does help reduce the number of features somewhat. But what about the case where we have a bunch of different forms of the same word or idea? So like, for example, what if your vocabulary contains the words different, differently, differ, differing, and differed? So grammatically, these are distinct words, but conceptually, they're very similar. So we might want to combine all of them into a single base form, like differ, or depending on how aggressive you want to get about it, even diff. This is what's known as stemming. And like with stop words, there are a lot of off-the-shelf options for this, including built into Scikit-learn. So stemming is desirable not just because you want to reduce the size of the feature space, but also because you could potentially lose information otherwise. We want the classifier to recognize that if there's a document that's talking a lot about differ and a document that's talking a lot about differing, they're very similar conceptually. We as humans get this intuitively. We have to find a way to build this information into our model as best we can. So once the stop words are removed and everything is stemmed, there's still kind of one more major issue, and that's that it's not really desirable to just use the raw word counts because they don't give us a good idea of the importance of the term. So it's easy to think that if a term appears a lot in a document, it must be very important. However, depending on the domain, it's possible that that term appears a lot in many or most of the documents in the corpus. So a better idea is to find some way to weight the terms. And a really popular way to do that is what's called term frequency, inverse document frequency, or TF-IDF, as you might have heard it. As you can tell based on the name, there are two components to this statistic. So the first is term frequency, which is just that raw count from earlier. And there are more sophisticated ways than just doing the count, but this is the simplest. And the second term is going to be inverse document frequency. And this decreases the importance of words that are very common in the corpus and increases the importance of those that are rare. So IDF is going to be obtained by dividing the total number of documents by the number of documents that contain that term, and then logarithmically scaling the result. So then the TF-IDF is going to be the product of these term frequency and inverse document frequency terms. And the way you'd interpret it is that a word that has high TF-IDF is going to appear a lot in that document, but not as frequently in the whole collection of documents, and then vice versa if it's low TF-IDF. So here's a quick example of what this whole process would actually look like. So you're going to start with your text. You want to remove things like punctuation and capital letters and so on. You want to get rid of stop words as the first step. So the, are, and from are going to disappear from the sentence. Then you want to apply your stemmer. So this would be the result of what's called the Porter stemmer, which is a common algorithm, but there's no one set way to do stemming. So there are other options as well. And then finally, you'll apply TF-IDF to convert into a numeric vector. So finally, at this point, once we've gone through this, we've got all of our documents, we'll have the vectorized documents ready to be fed into a machine learning algorithm. And so, like last time with the Cvc data, we tried a handful of the core classification algorithms provided by scikit-learn. You guys are probably familiar with a couple of these. So we use decision trees, a random forest, a neural network, simple feed-forward, naive Bayes, k-nearest neighbor, and an SVM. And again, like last time, we found that the support vector machine gave us the best performance. This wasn't really entirely surprising to us. There's a lot of support in the literature that says that SVMs tend to, in general, perform well at natural language processing tasks. So using our cross-validation process with our labeled data, we were able to get about 76% classification accuracy here. And we found that using the abstract instead of the title gave us slightly better performance, which intuitively makes sense because titles are shorter, so they could be potentially missing keywords that were in the abstract that were important to the document. So initially 76% might seem like kind of a step backward here. If our CPC classifier was at 87%, why would we be excited about something else that at first glance looks like it's about 10% worse? Well, so our hypothesis here was that these two models are going to be capturing different characteristics of the patents, so theoretically they could be combined to achieve higher accuracy together. And recall that earlier we were talking about ensemble classifiers, which are built around this exact idea. So with this in mind, we proceeded to come up with a third model to leverage the information from the first two. So the third model is pretty simple. For the inputs, you take the outputs of those two component classifiers, convert them to numerical codes, and stick them in a vector. So the patent's going to start out represented as a handful of CPC terms in a text abstract, and then at this point, it's going to be a 2D numeric vector representing the industry categories that our two component classifiers assigned. A lot of times what underlies an ensemble classifier is going to be something like some sort of weighted voting scheme or something similar. We decided to try something a little bit different, and funny enough, this was originally intended to be just a prototype, like we were just kind of throwing stuff at the wall to see what stuck. But it worked well enough that we actually continued on with it. This is what we used. So what we did is we used these vectors as inputs to a type of classifier, which is called a decision tree. And the idea here is that you're looking to sort of construct a flowchart by splitting the data in the ways that are going to give you the most information gain. And this information gain is going to be defined relative to the entropy of the data, which is a concept from information theory that's going to reflect how much a split in the data set is able to divide the resulting partitions into different classes cleanly. So building a decision tree is the process of algorithmically choosing splits in the data based on feature values with this goal of entropy reduction, treating those splits as nodes and edges in a tree structure, and then continuing this process until the leaf nodes correspond to the class labels. So this would be a quick example that's more intuitive than our applications. Say you wanted to find out if it was a good day to go hiking. So you've got a binary outcome variable, which is just yes or no. And then let's say that the features you have for your weather data are the outlook can be sunny, overcast, or rainy. And then the humidity and the wind can both be high or low. A possible tree constructed by the algorithm could look like this. And so let's say that the biggest entropy reduction from the split could result in splitting on the outlook values first. So let's say an overcast day is almost always going to be good for hiking, so that goes directly to a leaf node for yes. But if it's sunny, then maybe we have to further partition the data to reduce the entropy based on the humidity. So if it's sunny and humid, hiking is probably going to be kind of miserable. But if the humidity is low, then even if it's sunny, it will probably still be a good day to go hiking, and so on. So in our case, the features that we can split on are the industry categories output by our component classifiers, and the outcome variable at the leaves is going to be the final industry category that we're going to assign to that pattern. So our algorithm is going to be choosing splits in the data to minimize the entropy relative to that correct classification. So that way when we get a new pattern in, we can just run it through the first two classifiers, feed that into this third one, and then essentially follow it down the branches of the tree until we get to a leaf that corresponds to the final industry category that it's going to be assigned. So it's worth noting that the decision tree algorithm can be really prone to that overfitting problem we were talking about. And one of the best ways to avoid that is to favor constructing shorter or smaller trees. Luckily, because our number of features is really small at this stage comparatively, it's not much of a concern. However, it does explain why this algorithm tended to fail pretty spectacularly on the two component classifier problems, because those had comparatively many, many more feature values. So using these classifiers chained together in this way, and by the way, the term for this type of ensemble classifier is called stacking, we were able to get 98% accuracy using cross-validation. So this was able to confirm what we were thinking, that the CVC classifier and the abstract classifier were in fact capturing different information about the patents, and combined it was able to give us a pretty vast accuracy improvement. So at this point we had a working model, and after running some data through it to kind of sanity check our accuracy results and make sure we weren't overfitting, we were ready to turn it into an actual microservice-ish thing. So I already mentioned that we largely developed in Python. It's a popular choice for data science, and previous attempts with R haven't really worked out. And it also allowed us to make use of libraries like scikit-learn. So we decided to use a micro framework called Flask, which many of you have probably heard of. Along with Django, it's one of the more popular web frameworks for Python. And then at this point, we were able to use JSON requests to either provide data for retraining or send over test instances to be classified and wait on the response to the correct classification. The other nice thing we were able to do because of this is to make use of Python's pickle module to persist our trained model. The expensive part of this whole process is that processing of the training data and then training the model. So if we can avoid redoing that until we have new training data to add, or we want to add a new category, or whatever the case may be, that saves a lot in terms of efficiency. And I should note that even though I say the training is relatively expensive, it still happens in a matter of seconds or minutes, not hours or days like can sometimes be true of machine learning processes. So this still ended up being fairly quick. So then our last step after all this was to containerize the app, and we used Docker for that. And then we gave it a name, Sybil. So the Sibyls were ancient Greek oracles. The picture in the middle there is actually a painting of one of the Sibyls from the Sistine Chapel. So we thought this was kind of cute because, much like an oracle, Sybil is intended to make predictions. So we got Sybil up and deployed, and just like that, the tedious process of hand categorizing patents was no longer an issue for us. So after hearing me step through this whole process of developing Sybil, you might be thinking that this all seems kind of simple and straightforward. And if you feel that way, I want to take a minute to set the record straight and say that you're absolutely correct. And this is really at the heart of why I wanted to share this story in this setting at this conference with you guys. So the techniques I've mentioned here, these are all things you'd at least hear mentioned in any good upper-level machine learning course at pretty much any university. And unlike in academia, where the push is always for kind of new and more intricate and complex approaches, in industry, we have the luxury of only needing to make things as complicated as they have to be to give us the results we want. So that's why, however simple the approach, this did end up having really real results for us. So not only was it able to automate a really time-consuming and inefficient task that we faced as an organization, it also serves as a building block for more complex solutions that we currently have in development. So for example, consider this, recommender systems, the engines behind like Pandora, Netflix, Amazon, whatever. These are at core just a special case of a classification problem. So by gaining knowledge about how patent data can be leveraged for classification in this instance, we've already taken major steps toward a goal of developing recommender systems for these technologies. So throughout my now 5 years in the data science and machine learning world, I've had a lot of conversations with people in tech companies, both within and outside Montana as well. His attitude toward data science or machine learning, or whatever you want to call it, is essentially like, oh, well, we're not ready for that. We're not Google. We're not IBM. That's way beyond us. And to that I say, like, hey, so neither are we. TechLink isn't even a software company, actually. But as we've shown here, you can still benefit from this in a really real way. If you have data and you have questions that you want to ask about it, then as far as I'm concerned, you're ready to move into this. I think companies kind of end up doing themselves a disservice by thinking that machine learning is this like enigmatic, possibly complicated thing that's really just mostly going to stay in Silicon Valley. The fact of the matter is that we have the talent here in Montana to pursue more of this, and really we only stand to gain from it. So according to LinkedIn's 2017 Emerging US Jobs Report, data science and machine learning jobs are the fastest growing on the market. And in fact, I do have to interject, bar instructor is one of these, which I love. But if you zoom in further, in fact, of the top 5 data science related positions account for 3 of these. So companies shouldn't be allowing themselves to be left behind just because of a misconception about what these concepts mean and who they're really applicable to. So if this talk has you thinking about some potential opportunities, in your own company or your own project, I really encourage you to pursue those. Talk to your team members, your team leads, your supervisor, reach out to local people with this kind of expertise, collaborate with the university if you can. Whatever you do, there's a chance that it could potentially mean very real results for you and your project.